Technology revolutionizes the way we live, but insecure, negligent, or exploitative technological advancements are threatening global security and stability as we speak. I'm Stifel, the Chief Strategy Officer at the Institute for Security and Technology. We're a 501c3 critical action think tank that unites tech and policy leaders to create solutions to these emerging security challenges. Welcome to TechnologIST Talks.
I'm Steve Kelly, Chief Trust Officer at IST. We will sit down with entrepreneurs, venture capitalists, and policymakers to learn about the real-world challenges they face in accelerating innovation across biotech, quantum, energy, and other critical technology areas. We'll get their takes on the policies that help or hinder their progress and discuss where they see things heading.
So if you're interested in how technology, policy, and security come together, you're in the right place. Welcome back to TechnologIST Talks. I'm Stefan, Chief Strategy Officer at the Institute for Security and Technology, and your host today. I recently sat down with Stefan Leichenauer, Vice President of Engineering and a member of the inaugural team at SandboxAQ, to learn about his work transforming theoretical concepts into tangible, real-world applications. We discussed the current state of play in the quantum industry.
Really, if we start at sort of the base level, like fundamental scientific challenges, those were solved a long time ago. There's no fundamental scientific issue that gets in our way. There are some things that we don't quite know how to do yet, like when we talk about building a scaled quantum computer that can tolerate errors and be able to tackle large computations. There are still a few challenges left to tackle.
We break down the potential use cases for groundbreaking quantum technologies.
So one example is using advanced quantum sensors that can be very sensitive to the magnetic fields that are created by the Earth, geophysical magnetic fields, influenced by the rocks and things that are all over the place. And these create kind of a magnetic fingerprint across the whole globe. And if you had a map of that fingerprint, which those maps exist, and you had a sensitive quantum sensor that could pick up the tiny changes in magnetic field, the magnetic field fingerprint as you move from place to place, and you had the software, the AI-powered software that could isolate that signal and get rid of the noise, then you'd be able to figure out where you are in a completely self-contained way.
And we unpack the differences between the United States and Chinese quantum industries and how China might pull ahead in the race for new tech.
And I think there's more than just the money. There is a significant amount of dialogue around these aspects of quantum technologies, around different aspects of quantum technologies, and trying to build bridges between different organizations so that we're not all just trying to pursue these goals in silos, right? We should be working together.
How did SandboxAQ begin? What are the near and long-term challenges to unlocking the full potential of quantum computing? And what are Stefan's hopes for the future of quantum science? Join us for this and more. Welcome, Stefan. Thanks for joining us.
Thank you for having me. Happy to be here.
So, Stefan, you've been at SandboxAQ since almost the beginning. But before we talk about SandboxAQ and the work that you're doing there, I thought we might begin by going back to your roots a bit and thinking about your time in academia and transitioning from a research role at a leading engineering organization, university, to the role that you have at SandboxAQ, at obviously a leading quantum technology company. What prompted you to leave the ivory tower of academia and move over?
I was one of these people who, I always said that I was lucky, and I was lucky, that I always knew what I wanted to do. And the thing I wanted to do was become a scientist, and then becoming a scientist turned into becoming a physicist because I loved understanding how things worked in the most fundamental ways. And that has not changed. Even in this transition into industry, that's all still very true. But my original path was the only path that I thought was appropriate for a person like me. The only one that I kind of had my eyes on from the beginning was this academic path, becoming a professor, et cetera, et cetera. And I think what happened after I got far enough down that path, I got my PhD from UC Berkeley back in 2011 in theoretical physics. And I continued doing research in that area for several years after that in various research positions. And the realities of academia, the bureaucracies that you have to deal with, and basically It's not all just sitting around thinking fun thoughts all day. And really, the other thing that kind of prompted my move into industry was the fact that in this academic setting, as fun as it was for me to sit and think about equations all day, there's a very limited impact that you can have on the real world. And one of the things that I now have in an industry setting at SandboxAQ, and that many people have in this move from academia into industry, is that you get to see that what you're doing is having real world impact right away, or at least in the near future. And that's extremely rewarding. So I think that's a big change, I think, from the academic style of working, where, as you said, you're in this ivory tower thinking your thoughts, and it can be fun for people who are into that sort of thing. But being able to see technologies develop and then be used in the real world, it's rewarding in a very different and much more tangible way.
I definitely appreciate that. And I think that's, this is not a promo for IST per se, but that's where we sort of distinguish ourselves, we think, from sort of traditional think tanks, is that we're really trying to focus on the practical and the application of the topics that we address. And so we're, again, excited to have this conversation with you about quantum. So speaking of quantum, it's often seen as a long horizon technology, but I think at Sandbox, you are really focused on kind of the near-term applications. So can you share a bit about what prompted that focus for you on the near term?
Again, it really comes back to this North Star of impact. And there are many ways to have impact, right? But near-term impact is something that's very important to us at SandboxAQ. And so when I think about quantum technologies in general, people most often think about quantum computing. And it's true that quantum computing is a longer horizon technology, meaning certainly today it's not ready for real-world prime time impact on people's everyday lives. It's still a technology that's in development, and it will be for a little while longer at least. But there are other aspects of quantum technology that are not so long horizon. There are aspects of quantum technology like quantum sensing, for example, where we actually can have products out there today that use quantum sensing, modern quantum sensing, and are successful or can be successful at solving some of the grand challenges that are facing the world right now. And so at Sandbox, we have our eyes on all aspects of the technology from near term to long term. But in terms of where we put our focus, it's on near term applications. But the truth is that there are near term applications of quantum technology along with other supporting technologies like AI.
So in terms of kind of the nearer term and the practical applications for present day, near days, what do you think from a scientific perspective needs to happen in order to unlock the full potential of quantum computing? How quickly do you think we'll get there?
So there are a few things. If we look at quantum technologies broadly, there are a few things that need to happen, and you can divide those into engineering challenges and scientific challenges. Really, if we start at sort of the base level, like fundamental scientific challenges, those were solved a long time ago. There's no fundamental scientific issue that gets in our way. There are some things that we don't quite know how to do yet, like when we talk about building a scaled quantum computer that can tolerate errors and be able to tackle large computations. There are still a few challenges left to tackle. But before I get into that, let me come back to the things that can be used in the present day. So when I think about near-term applications of various kinds of quantum sensing, the challenges are much more mundane engineering type challenges, say system integrations, making sure that the quantum sensors, the little fundamental quantum nuggets that are doing very impressive science, are integrated into workflows and systems that support them, and they're part of a larger device that does something. So for example, a medical device, there's a lot. If you want to build a medical device that uses a quantum sensor at its core, the quantum sensor itself is only a small piece. And it's really about building out the rest of it, having the AI that's capable of running the device and processing the signal and extracting the signal and getting rid of the noise, that kind of thing. And so that's the work that's left to do for near-term applications. For long-term applications, there's, especially in quantum computing, there are several milestones left to tackle having to do with error correction and scaling up and things like that.
drilling down a little bit on the kind of thinking about the applications, assuming that some of these kind of nearer term and longer term challenges are overcome or at least reduced. And thinking about, in particular at IST, we look at the intersection of public-private partnerships and the collaboration between industry and the government as it can impact national security and how it can be both used for national security and how, where there's not significant consideration given, kind of the negative impacts that can have on national security for failure to take account of some of the risks of technologies as they're evolving. If you think about the critical strategic areas for governments, from advanced quantum sensors that could obviously aid in precision navigation, climate sensing, there are obviously biomedical applications, and then thinking about complex challenges in material sciences and medicine, the answer could be all of the above. But is there, of those kind of opportunities, which of those excites you the most as we think about the role of any application from the government perspective?
It's true that all of those are very exciting. I think maybe one that's worth highlighting is the precision navigation issue that you mentioned. So just to say a little bit more about that, the primary way that people navigate and find their way, and it's not just a government thing, it's everyday people, is with their GPS devices all over. You have them in your phone, you have them in your car. But the way the GPS works is it involves communication with a satellite or with a collection of satellites orbiting the Earth. And that makes it vulnerable. It makes it vulnerable to jamming. It makes it vulnerable to spoofing. And we're seeing more and more each day that GPS interference is happening. And this is not just a concern. This is not just a national security concern. Of course, it's a national security concern, but it's also affecting, say, commercial airlines that are flying in regions, near conflict regions, for example, like near Ukraine or in areas in the Middle East. And it's a real problem. It's a real problem for everybody. And so where quantum technologies can come into play is through systems where you can figure out where you are and where you're going without having to communicate with a satellite. So one example is using advanced quantum sensors that can be very sensitive to the magnetic fields that are created by the Earth, geophysical magnetic fields, influenced by the rocks and things that are all over the place. And these create kind of a magnetic fingerprint across the whole globe. And if you had a map of that fingerprint, which those maps exist, and you had a sensitive quantum sensor that could pick up the tiny changes in magnetic field, the magnetic field fingerprint as you move from place to place, and you had the software, the AI-powered software that could isolate that signal and get rid of the noise, then you'd be able to figure out where you are in a completely self-contained way without having to communicate externally with a satellite while you were traveling around. And that's an example of a technology that certainly has national security applications, but every commercial airplane should have this kind of thing. So that's very exciting. That's one of the things that we work on at Sandbox is this magnetic anomaly-based navigation systems, which we've been able to demonstrate work in real time. And it's actually a thing you can do today.
So there you mentioned AI. And so thinking about the role that AI plays as an enabler in quantum technologies, in what ways do you see quantum computing advancing where in areas where AI might fall short? I think you were just talking about them being, I wouldn't say two parts of the same coin, but two halves of the same coin, but certainly key enablers. Are there areas where you think advances in quantum can outpace, if you will, AI, or will they always be intrinsically linked?
There's nuance to this question because it's not just a black and white, one or the other kind of thing. I think the best place to start is to think about, if we focus on quantum computing for a second, what do we think quantum computing is actually good for, right? What can it be used for? So one application is factoring numbers and cryptography and so on. And that had a lot of national security issues, but let's leave that aside for a second. The other area, primary area where we think quantum computing is actually going to make a difference, a real difference, is in applications of chemistry, quantum chemistry. So when we're looking for design new materials or drug discovery or things like that, fundamentally there are molecular interactions that we need to understand very well. We need to model very well. We need to create new materials at the atomic level, new drugs at the atomic level, or at least it starts with what's happening at the atomic level. And understanding what's happening at the atomic level seems like a no-brainer. This is what quantum computers are good for. But there are a couple of subtleties there. First of all, there's a lot we can understand without quantum computers, without needing quantum computers, about those atomic level interactions. Or at least for the last 100 years, we've understood a lot about what happens at the atomic level, and we certainly don't have powerful quantum computers today. And a lot of what we've been able to do is model those kinds of systems using ordinary classical computers, and that will continue to improve. AI will continue to be used for that. But there are certain problems, especially quantum native problems, like especially difficult to handle, especially thorny atomic interactions. The electrons are doing something very complex, and no amount of classical computing, whether you use AI or something else, will be able to really model what's happening with high precision, with high accuracy, when it gets complex enough, complex in the quantum sense. And those are the cases where the only thing you can do is use a quantum computer to model the system. And there are fundamental reasons why we believe quantum computers are just more capable for certain kinds of problems than any kind of classical computing, including anything you might want to do with AI. And so for those problems, for those hard cases, you would expect to use a quantum computer. And maybe there are some very complex materials that you'd like to design where you need a quantum computer to get the right answer. But even in those cases, the quantum computer handles that one part of the total workflow, right? This comes back to what I was saying earlier about integrating quantum technologies into larger systems that can enable them. So the quantum computer one day will handle the hard quantum part of that total workflow that, say, is designing that new material. There's a quantum calculation at the center that you want to do. But then the answer to that, posing that question and processing the answer to that question, will be done with non-quantum computers, with AI and so forth. So there are pieces where AI by itself won't be able to do everything, but it will always be the case that these technologies are working together. You won't have just a quantum computer doing everything on its own.
I definitely appreciate that. I had illustrations in my mind of Venn diagrams and concentric circles and the like. So the more simplified level there, that way of framing the approach to these two, I think what many sort of perceive to be recent and near-term capabilities, when in reality, these are capabilities that are sort of seeing their own revolutions every decade or so, but they've actually been around for quite some time, thinking about both AI and quantum capabilities. So SandboxAI has been around for less than a decade. As we kind of transition into thinking about a bit more about your role at the organization, can you talk a little bit about what your main goals and focus areas are for SandboxAQ?
We are a young company, but we have big ambitions. Like I was saying before for myself, the company also is in pursuit of impact, the biggest impact that we can have, solving the biggest problems that we can try and solve. And I think this is actually, this isn't just me trying to sound good. It's actually the case that we focus most on the impact we can have, and that we are a, quote, problem first kind of company. First, let's talk about what the problems are that we want to try and solve. Then let's try and solve them. And technologies like quantum technologies and AI and so forth, those are really good tools that can be used to solve problems. But let's not go around with a hammer looking for all the nails. Let's focus on what we want to actually do and then try and solve the problems. And so what do we actually want to do? I mean, the kinds of problems that we are currently today solving and making progress on solving include things like drug discovery, especially for things like neurodegenerative diseases, new materials, new kinds of catalysts for manufacturing, battery technologies, those kinds of things. Also, the quantum sensors applied to issues of navigation, GPS-free navigation, and medical devices. Plus, in addition to all of that, the major problems associated with how cryptography is handled. Everyone knows that quantum computers have a big effect on cryptography. It renders a lot of cryptography obsolete. And so how does one handle that? What is the response to that? And the response to that is an improved way to do cryptography management, how we handle cryptography in general, not just what cryptography we're using, but how we manage it, how we track it. And so all of those are problems that we're solving today at Sandbox and using whatever the best tool is for the problem.
So in thinking about that broad set of issues that you all are trying to tackle, to what extent did early days of Sandbox having originated within Alphabet impact kind of the areas of focus? And I think kind of the approach for the organization. Do you think there were unique attributes to Sandbox having come out of a larger company that other startups would not necessarily experience?
Sandbox has a unique history, I think, a relatively unique history among all the startups, because we incubated for a while, for lack of a better word, inside of Alphabet. And our time at Alphabet was one of exploration. We were not a big team. For most of the time, we were less than 10 people. And what we did was we looked at a whole variety of problems and challenges facing the world. And we looked at how we could use emerging technologies like AI, like quantum, which were very clearly becoming important technologies emerging over the last 5-6 years. And we asked ourselves which kind of problems can be solved, and not just solved someday, but solved today. And so we were able to do that kind of exploration. And again, it was small scale. We weren't pushing out products at that time. We weren't doing a lot of business. We were just investigating. And when we spun out, the reason why we spun out when we did was because we were ready to take the initial ideas that we had, the prototyping that we had done, the investigations, and really we came across a few, the ones that I mentioned, which were ready to be scaled, ready for real application, ready to be developed in a more serious way. And that's when we spun out of Alphabet. And it was always the plan, by the way, to spin out, once we were ready, to spin out, create a company and go. And so we came out with, I guess, a head start compared to a lot of other startups. It's not like we began in a garage. So we had an advantage in that sense. And a lot of and I think I would like to say that we took some of the best parts of like the Alphabet culture with us, sort of an emphasis on innovation and an emphasis on applying technology where it's best. And now, since then, we've grown a lot. We're no longer less than 10 people. And now we really are applying some of these things in the real world, turning these ideas into real products and having real impact.
As you all are evolving as an organization and thinking also about your transition from academia into the private sector, focusing specifically on quantum, do you see multiple specialized providers working on quantum technologies, or do you think there will be kind of consolidation the way there sort of is around cloud and a few other computing capabilities?
Quantum may not be super special in this regard compared to other technologies. It's common for, at different phases of when technologies are being developed, for there to be times of expansion and times of contraction. Times of expansion in the sense of lots of different companies trying lots of different things, startups appearing, and then times of contraction where some go out of business, some pivot, some consolidate and end up as part of larger corporations, that kind of thing. And so that will play out and is playing out in the quantum space. I would say when it comes to things like, it may not be uniform across the different aspects of quantum technologies. When it comes to something like quantum sensing, which doesn't always get the attention it deserves, many of the sensors themselves are coming closer and closer to not quite commoditization, but are on that path where it's not just one person who knows how to build quantum sensors, and it's not like each one costs $10 million and requires a big capital investment. And so folks who want to do quantum sensing, it doesn't have to be concentrated anywhere. You can take quantum sensors and incorporate them into a lot of different products. When it comes to quantum computing, the story might be a little bit different, because building a large-scaled quantum computer requires a lot more capital investment. It's the kind of thing you can only do if you have a lot of money to spend. But more than that, it's unlikely anytime soon in the foreseeable future, or perhaps even beyond, that quantum computers will be anywhere near as ubiquitous as classical computers. Not everyone is going to have a quantum laptop, for example. Quantum computers are, in a more fundamental way, naturally cloud-based kinds of systems where they live in data centers where they can be maintained, and then you access them through the cloud, and there may not be that many of them total, at least in the foreseeable future. And so that lends itself well to more of a concentration of the technology.
As we think about the various quantum applications, do you see major differences in the investment landscape between the areas? We want to talk about that for SandboxAQ, but perhaps sort of more generally, how you see organizations focusing their investments.
There's certainly a lot of investment, at least with some organizations, especially, big organizations like IBM and Google and so on. They're investing a lot in computing, and various governments are also investing a lot in quantum computing. And so it seems like slowly but surely, quantum computing is a thing that will be done, at least by some of the big player, whether it's government funded or in private industry somewhere. But there deserves to be more investment in other aspects of quantum technologies, like I've already mentioned sensing many times. One of the things that's going to catalyze that, actually, which hasn't quite happened yet, but we're on the cusp of, is when we see the real world applications start to come to fruition. A lot of what's happened in quantum technology so far has been more and more development of the technology. There's new milestones and benchmarks being reached, and okay, there's more qubits, okay, there's this kind of tech demo, but we're not quite to the point. We're very close, but we're not quite to the point where we have really wide appeal commercial products that make a real difference, that incorporate some of these quantum technologies that are on the cusp. And once that happens, the flywheel of commercial investment in things that can be sold will kick into high gear, and we'll see a lot more investment from that point of view.
You mentioned we, and you mentioned nation states. And so I do want to touch a little bit about, I'm thinking about China and the approach that they're taking to quantum technologies and quantum capabilities. How do you see the relationship and sort of if there's a race? I was listening to a different podcast where someone was drawing a bit of an analogy, but as sort of like to Sputnik. And obviously that was a different nation state. But do you see the race that way at all? Or?
So China is an interesting one when it comes to quantum technologies. They've long made it clear that for them, quantum technologies are a strategic investment of national importance. And a lot of that stems from national security related issues, not just quantum computers to crack cryptography, but also quantum-based communication methods like quantum key distribution, QKD, which China has invested in for a long time now. They have been launching QKD satellites like the Messias satellite in order to create a quantum communication network. And their strengths began, I think, in that area, but that was, I think, almost 10 years ago when they launched that satellite. And this sort of optical aspects of quantum technologies, starting with communication, was a strength. But since then, they've definitely been extending into other areas beyond just optical approaches. So different kinds of methods. There are many different methods, modalities that you can try and use to build a quantum computer. And China's doing a lot of that. Their government is investing significantly in quantum technologies. Well, as of today, I would not say that China is ahead when it comes to developing these kinds of technologies. The best instances of quantum technologies are still in the Western world, but the gap is closing. And it's not a secret that they're investing a lot of time and energy and people and money into this area. And they expect to be the leaders, I think. And that may happen.
You touched a little bit about some of the advantages that they potentially have, thinking perhaps about a workforce that could be skilled up to address some of these and focus on some of these technologies. Do you see there being disadvantages for their approach and kind of their amassing quantum capability?
So the main disadvantage that they've had so far, historically, has just had to do with where the innovations are actually happening. Like they don't have a strong history of innovating in, being the first to do something, being the first to develop a new kind of technology. That gap is closing. It's only a matter of time before they are the first. They're sending a lot of the students, a lot of Chinese students are being educated in the West. They go abroad to Western universities. They learn things. They learn the latest techniques, and then they go back home and apply those techniques and further develop them. There is also a perception, I don't know how true it is, but there's a perception that some decisions being made at the top, say, in China, that can have a big influence on what happens throughout the country. Maybe there's too much top-down control. And certainly in the US especially, there's not a lot of top-down control. Everyone can decide to do what they want. But I'm not sure that that's really true. I think it's more like there's plenty of people doing things and innovating, and there's Chinese startups and all of that doing things that they think are best. And the winners get extra boosts from the government. And they're very serious about finding those winners and making sure that they have a few winners in their country. So whatever disadvantages they have, I think they are disappearing and may not end up being that significant. So it's a very serious, for those who are concerned about China taking the lead in quantum technologies, it's a very serious concern.
If I can ask just a brief follow-up question here, it's not so brief. They have reportedly planned to build a fully entangled quantum network. How do you see that as a sort of a challenge or an opportunity, or sometimes they're both, goal sets for the global quantum development?
So the reason why you would build a fully entangled quantum network is for purposes of secure communication. If you want to send messages, right, and you don't want people to be able to read them ever, then the only way to do that we know of, that is just guaranteed by the laws of physics to never be able to be interfered with, your message will remain secret forever, is through quantum communication methods. And this is something that China is very interested in, and this is the main reason why they're building this network. And so once they build it, and if it's successful, then that'll be a serious security advantage that they'll have. Now, I immediately have to list a bunch of caveats, because if something is in principle very secure, that's one thing, but the realities of the implementations of such a thing, there will always be imperfections, et cetera, et cetera. There are plenty of arguments that this kind of thing is not actually a good idea from a security perspective. I don't have a strong opinion on that, but what I would say is that having such a network as part of your secure communications strategy, maybe not just the whole thing, but as another layer of your secure communication strategy, it certainly makes it much more difficult. It's another thing that an adversary would have to get through in order to read your messages. And so this is the main goal of having that network. There are other reasons why you would want to have the network as well, say for distributed large-scale quantum computing, wiring together in a quantum entangled way different quantum computers in order to effectively make a larger quantum computer. It uses the similar kinds of technology, and so that it helps there as well. But to the extent that this technology makes its way to the rest of the world, it will, of course, drive forward everybody's quantum technology development. But to the extent that the main reason they're doing it is for their own national security concerns, they'll try and keep a lid on the most advanced aspects of it.
And talking a little bit about China, we're going to spend a few more minutes in a second here talking about the United States, but kind of as a bridge between those two, do you see there being domination by one particular country as it relates to, I think quantum technologies is too broad of a bucket, so to speak, but let's go with it for a moment here. Or do you see there kind of being, perhaps in certain applications, there are global leaders, but overall there isn't one kind of country who's ahead on all of the areas we've been talking about?
I don't think it's controversial to say that the US and China are the two global leaders in these areas. Until, I think, very recently, most or all of the quantum computers that were being built or that existed were in either the US or China. And I don't see any reason why it won't continue to be the case that those technologies are most advanced in those two countries. It may be a case, or it will probably be a case, where there is one or two countries that are the leaders and are the first to have scaled versions of quantum computers, or are the first to do this or that. And then later on, it will make its way elsewhere. That happens with many technologies. I don't think quantum technologies are particularly unique there. But it is true, though, that right now the US and China are the leaders.
So in terms of thinking about the US as one of the leaders, how effective has the US government been in thinking about operating as a partner in scaling and advancing quantum technologies?
The US government has definitely taken several important steps toward developing not just quantum technologies, but an ecosystem to further the development of quantum technologies. So a big step was taken back in 2018, the National Quantum Initiative, which put more than $1 billion into quantum technologies and established the QEDC consortium, where industry and government and universities could interact and communicate with each other when it comes to these technologies. And the places like the DOE, the Department of Energy, and NIST, the National Institute of Standards and Technology, were given funding specifically to go toward quantum technologies that went into government labs and so forth. More money was given with the CHIPS Act in 2022. And there is, I believe now, another big, maybe close to $2 billion proposal working its way through Congress to renew the National Quantum Initiative. So it's billions of dollars, at least a couple of billions of dollars is going into it. And there's from the US government. Now that's less than what the Chinese government is putting in, but it's still significant. And I think there's more than just the money. There is a significant amount of dialogue around these aspects of quantum technologies, around different aspects of quantum technologies, and trying to build bridges between different organizations so that we're not all just trying to pursue these goals in silos, right? We should be working together.
Strong concur from us on that point. In thinking about the areas where you think the U.S. really needs to maintain its focus to keep its current leadership position, are there areas that come top to mind to you?
So there's the U.S. alone, but then there's the U.S. together with its allies. And part of maybe what the U.S. should do is think through how it wants to be interacting with its allies when it comes to quantum technologies. So what do I mean by that? A lot of the components, say, that you would use to build a quantum computer are under export control because, well, they can be used for international security. And regulations like export control and other more serious regulations around when certain kinds of technologies are allowed to cross borders, those are things that are very important for consideration, especially when it comes to crossing borders with our allies. There's a risk that we close things off too much and take too much of a US-centric point of view and lose the ability to collaborate fruitfully with folks who we have collaborated with in the past, or especially at the academic level, at the university level. There's a lot of international collaboration, or there should be a lot of international collaboration. And there's a risk that we close things off too much for the sake of national security, and through that we slow down the process and end up losing out overall. I think that would be the main thing that I think deserves careful attention. I'm not saying that there should be zero regulation or that we should just allow anything to go, but I think it's one that deserves monitoring and attention. Another thing that the US government can do and can continue to do is create an environment where universities and industry can succeed and collaborate and work with each other without the government itself doesn't have to be directly involved, but creating an environment where innovation can happen and where companies and startups are rewarded. There's, say, grants and things available for them where they can develop things that they can then take to market, is a way to foster innovation within the country.
So are there current examples that you think are public-private partnerships along the lines you just described that should be kind of replicated, or is this something that you're not seeing happening yet?
Well, I think it's happening to some extent. So I already mentioned the National Quantum Initiative. A lot of the funding for the National Quantum Initiative is for or goes effectively to what amounts to public-private partnerships. For example, a lot of the national labs are working on the fundamentals of a lot of future technology. And these national labs are empowered to some extent to work with private sector companies to do technology development. And in those kinds of situations, it's always a little bit tricky to deal with questions of IP and so forth. Like everybody wants, the IP is very valuable. And so that can end up being a sticking point. But in general, these kinds of activities are happening. There could be more, like we could put in 10 times as much money and have 10 times more happening. But I would say we have a start.
I'll take that as ending on a positive note. That's all the time we have for today's discussion, but I really appreciate you, Stefan, coming on and talking with us about your work at SandboxAQ and how you see the quantum technology ecosystem evolving.
Again, thank you for having me. It was a lot of fun.